In the last video, we discussed the fact that charge drifting in a single direction is equivalent to electric current. Having one basically means you have the other. But is there some way to harness the power of this electric current, or rather to control it? We said that the unit for current is the ampere, or amp for short. Then if we specifically wanted to have a current of say 10 milliamps through some device like this LED here, how would we accomplish that? Or what about 20 milliamps? Do we just connect a battery across it and hope for the best? Clearly, we need to think this through some more.
She said, "Oh man, the building is on fire." I said, "No, what? I got my 3 kids and we bounced out. We ain't gonna be in no fire, not today."
We should start by recalling our expression for the drift velocity. The average current in a wire is just the number of charge carriers per unit volume times the charge per charge carrier times the cross-sectional area times the drift speed. Well, an important electrical property we can define is the current density, J, which is just the current per unit area through a conductor. If we take the current and divide it by the cross-sectional area, we get the current density, which in this case is just the number of charge carriers per unit volume times the charge per charge carrier times the drift speed. Now, George Simon Ohm comes along, and he notices something really interesting that happens in some materials. It turns out that in many conductive materials, the current density in that material is directly proportional to the electric field induced inside that material. This proportionality constant, sigma, it depends only on the material itself, and it's different for each conductive material. Sigma is called the conductivity of the material that we insert, and it's not to be confused with the surface charge density we've defined previously, which we also called sigma. Don't worry though, we won't be working with conductivity all that much after this video. Now, this relationship we see here that Ohm is credited for discovering, it has very profound implications as we're about to see. In fact, the relationship itself is so important, it has a name. We call it Ohm's Law. But once again, this relationship is true for many materials, but not all of them. So for materials in which this property does hold, we say those materials are ohmic materials. For other materials that don't obey Ohm's law, we call those non-ohmic materials. Now let's ask, what if we have a potential difference across an ohmic wire? Maybe we say this wire segment has a length L. In that case, we remember we can write the magnitude of the potential difference as E times L, where the electric field is a result of the potential difference. A potential difference between the two wire ends creates an electric field within the wire. Recognizing that E is just J over sigma from the top equation, we can plug that in for E into the expression for the potential difference, and we end up with this. We also remember that the current density J is just the current divided by the cross-sectional area of the wire. The potential difference across the wire segment is then a function of the electric current in the segment and 3 other variables: the length of the segment, the cross-sectional area of the segment, and the conductivity of the segment. What we note here is that the length, cross-sectional area, and conductivity of the wire, these are all variables in our control, right? The length and cross-section of the wire depend on the geometry of the wire, which we can change. And the conductivity of the wire just depends on the material we use. That we can also change at our leisure. Then what's usually done is we take this mixture of all 3 of these variables and lump them into a single variable denoted with a capital R. Then we can say the potential difference across this wire segment is just the current measured across it times this new variable we've just defined called capital R. Capital R is what we call the resistance of the wire segment. It's defined by the potential difference across the segment divided by whatever current is measured through the segment. And this actually provides us with an answer to the question we posed in the previous video. How do we control the amount of current going through any specific conductor? We do so by taking advantage of the geometric or material properties of the conductor. By choosing our wiring elements carefully, like the length, thickness, and material, we can create any resistance we want, which means we can create any current we want. Remember, potential differences are usually in our control too, as they just depend on how we design our batteries. More on that later. We have 9-volt batteries, for instance. Now, what are the units for resistance? Clearly, resistance has units of volt per ampere because we have potential difference divided by current, but resistance also has its own special units, denoted with a capital omega. This is called the ohm, named after this guy here, and it's defined such that 1 ohm is equal to 1 volt divided by 1 amp. Now, just one last thing to go over. You remember how I said we won't really be dealing with sigma anymore? That's because what's usually done by convention instead is to call 1 over sigma the resistivity, rho, of whatever material you're working with. Then we recalled that the resistance could be written as L over sigma A, but the more common expression you might see in your class is rho L over A, where rho is the resistivity here. Now let's figure out what the units for resistivity are. We know resistance has units of ohms, length is just meters, and area is meters squared. That means resistivity has units of ohm meters. And that's all to see here, folks. Resistance is our gateway into the world of controlling electric current, and that precise control allows us to create virtually every electronic device you've ever seen in your life.